Okie dokie. All right, so we have two topics to kind of review today. We've got particles work energy and particles conservation of energy. And I went over and over and over in class that work energy we can always use, but conservation of energy is the equation that we can only use if there are only conservative forces doing work on our system. Okay, so if you're unsure, maybe use work energy instead. All right, so I've got two problems. As we normally do, I'm going to let y'all take a stab at them first, and then I'll hop in later. So let's see. We've got this pulley system, two pulleys. This thing in the middle is not actually a pulley. This is just a ring that is connecting these three ropes. So this ring is able to sink down as A falls down and B and C go up. So A is a 12-pound block, and it is released from rest. As it's released from rest, it lifts the two 15-pound weights B and C. So both B and C are 15 pounds. So really this problem is perfectly symmetric, even though I think they, is it just my eyes or does C look smaller than B? I think it might just be my eyes. But anyway, it's perfectly symmetric. Determine the maximum distance that A will fall before its motion is momentarily stopped. Neglect the weight of the cord and the size of the pulleys. Okay. I'm gonna leave you there. See what you're able to do. It's all in pounds.
So we have to divide by gram
to get mass.
Okay.
Yes.
Are you going to post the practice exam or anything for the? Do you know when you're going to do that?
I certainly can't do it today. I have back-to-back meetings from 8 to 5, but
I'm just wondering if it's going to be over spring break, like if it would be posted.
I don't know if I'll get it out before spring break, but certainly over spring break at the very least. Yeah.
I just wanted to start studying that.
Makes perfect sense.
And then were the solutions for the last exam? Did you post those?
No, for continued reasons, but I'll post it right.
Okay. Well,
it's okay. It's okay. Do you guys have the problem right now?
Yeah.
Hey, Giovanni.
Hello. Yeah, the sides are perfect.
Yep. Oh, sorry, you.
Yeah.
Just give me 2 seconds.
That's okay.
It's posted in the Welcome to Dynamics module.
Okay.
Questions?
The free body diagram.
Yeah,
I
so
know what is, we can look for, I'm just gonna sometimes draw it for the.
yeah. Yep, that makes sense. Okay, so what I drew, it's I didn't actually draw a free body diagram, but I did draw a diagram that shows me like the geometry of what happens when it starts to sag. And then I gave myself some like intermediate variables to help me with that trig problem. So the most important is to give yourself a name for how much it drops. So that's what I call Y. So it's 4 feet. So it's 4 feet. So the reason I say this is not really a free body diagram is because I'm not actually drawing any of the forces. The only forces that are in this thing are tensions and weights. And from the example problem we did in class, we realized that for this pulley system, all of the tensions are internal to the system if we treat all of it as a system of particles, right? So if we say that we're going to treat this as a system where we're summing all of the kinetic energies for A, B, and C, then we don't need to worry about tensions in the work part of the problem. So in that case, the only part that we do need to worry about for the work is the weights, which are pretty kind of simple because we know A is going to be going down because that's what the problem asks us about, which means that B and C must be going up. Where are you stuck, Micah?
Yeah.
Where?
Yeah, I get the rope equation. I don't know, I'm getting too many variables.
Okay. Tell me about your rope equation. What'd you get?
Okay, so I did essay just like that, like half of it. So I did 2A plus 2B plus C.
Like that? Okay. And then what? Derivative?
Dot B equals negative S dot A.
Okay, so I've done this before. This is another example where it's good to, instead of thinking about time derivatives, think about like
Delta.
deltas,
Okay.
right? So there's no change in the length of the rope over any delta, right? So delta L rope still equals 0. Equals 2 delta SB plus 2 delta SA plus 0. Okay. Is there, can we maybe not bring theta into it?
So it's just in terms of SA and SB. Or in 4.
And 4 and y. So I see a triangle that looks,
Oh, yeah.
so delta SA is going to be the final length of SA minus the original length of SA. Right, the final length of SA should be the square root of y squared plus 4 squared by Pythagorean theorem. The initial length of SA was that 4 feet. Another thing you might notice is that your 2's cancel out. So you wrote the rope equation as if you considered both sides, this side, this side, this side, and this side, but really you could do it all with just half of it. So just the part I highlighted in purple on my diagram. Y'all remind me of the work energy equation?
Sum T1 or versus T1.
Yep, sum of T1.
T1 plus the sum of U1 to 2.
Good.
And equals T2.
Very good.
Is this equation going to equal 0?
Why?
Because it starts at rest and then it ends when the block A stops moving. Or like when the displacement when A is stopped.
Yep, so it starts from rest and it ends at rest. Yep.
you explain one more time why the rope equation cancels out the twos? Like, shouldn't it still be 2 for B and C? Like, because you have 2 ropes here and 1 rope here, so it's like 2 to 1. Because you can look at just one side, but then you'd have to double the weight and the tension.
The weight and the tension have nothing to do with the rope equation.
Well, yes, but in that case, there's 2 ropes, one holding the B and one holding the C. And there's only 1 rope holding the A.
Okay, but we're trying to write an equation for the length of the rope, right? And because this thing is perfectly symmetric, however much B goes up and down, C will go down up or down that same amount. So if you wanted to write the rope equation the way that Micah suggested, you could write it as this entire rope is 2 SB lengths, one connected to block B, one connected to block C, plus 2 SA lengths, one on either side of A. So we can write it like this. Or the way that I did it is I said honestly and truly, this is 1 rope. And this 1 rope must not change length. That's all I did. You could also say this is 1 rope. And this 1 rope may not change length. Either would give you the same answer. Because the way we have it written, the 2's cancel out. And you get the half rope problem.
Even if you consider it as one big rope, all your values will be doubled, so it will still come out to the final answer.
Yep, that's what I'm saying. Where these 2's cancel, 2 on one side and 2 on the other side. Is that what you mean, Samuel?
Yeah, if that helps.
Okay. Okay, so how can we write an expression for the work done by the weight on block A?
Gravity times SA.
How much does SA drop? Or sorry, how much does block A drop? Does it drop by SA?
Oh, no.
It drops by Y. Very good. So we have mg, which is really just 12 pounds, times Y. That's block A. And it's positive because gravity points down and it's asking us about this thing dropping. So the movement is in the same direction as the force, so we get a positive work. The next part is what's a little bit trickier. So 2 times the work done by either block B or block C. So the force of gravity for both block B and block C is just 15 pounds. And then how much does this displace? Right, the delta SB tells us how much the block B displaces. So it's square root y squared plus 4 squared minus 4. And is this positive work being done or negative work being done? Negative, because the weight pushes down, but blocks B and C are moving up. So we get a minus this term.
How do we know we don't need to involve tension in the equation?
Whenever the tension is fully within that same system of particles. So if we had, for instance, wanted to analyze just block B or just block C on its own. And we didn't write this as a system of particles. We would have to include tension because now tension is entering this system that I've just highlighted in blue. It's entering this system as an external force,
Okay.
right? But when I include the system as being everything here, 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 and here, all the tensions, both the tension at one side of the rope and the other side of the rope, are canceling.
Okay, so even if you did solve it with tension, they.
It would
all
still come out.
Okay.
Yes. Yeah, exactly like the problem we did in class where I ignored the fact that we can technically ignore tension
Mhm.
and we found out that tension canceled.
Okay.
So it'll come out just fine if you forget.
Okay.
Yeah. Okay, so I'm seeing an equation with one unknown and one equation. There's a little bit of icky algebra, but we should be able to solve for y. There are two solutions. One of those solutions is 0, but the other one is really what we care about.
Got 3.79, would that be close enough? Okay.
Yeah.
Delta V.
For delta B, square root y squared plus 4 squared, all minus 4.
Is it not a negative out front?
Ah, so In our rope equation, what does the negative tell us?
This direction.
The direction of
Right, so
motion. Yes, yep. We set the negative here based on whether it's doing positive or negative work.
Yes.
So we did all of that logically instead of letting the negatives drive us. So one thing that I wanted to check, but I didn't get a chance to, was to see if this problem would have worked the same if we'd used conservation of energy. I'm not entirely sure that it would have because of the tension forces, but it might have. So what would be really interesting is if you went back and used the conservation of energy equation and just checked to see if it would have worked or not. But work energy is always going to be a little bit safer just because there's no kind of caveats. All right, questions with this one? Okay, all right, the next one I think is a fun one. If you like roller coasters. All right, the roller coaster car has a mass of 700 kilograms, including its passenger. If it is released from rest at the top of the hill A, determine the minimum height h of the hill crest so that the car travels around both inside the loops without leaving the track. Neglect friction, the mass of the wheels, and the size of the car, essentially just saying no friction and you can treat it as a particle. What is the normal reaction on the car when the car is at B and when it is at C? Actually, I'm not going to do this one. I don't think we have time to answer this, but we can find H today, and you can do this after the fact. Okay, so let's just solve for the height, the minimum height that the first drop has to be in order to get us safely through B and C. Okay. And then it gives you the radius of curvature of the track at point B and point C. Okay. Whenever you're given radius of curvature, what does that make you think about? What? Acceleration in the NT coordinates. Yeah, absolutely. So we will absolutely have to use the fact that the acceleration in the normal direction is equal to v squared over rho u hat n. So also, it's asking us about forces. So we know we're probably going to have to sum forces. So what's going to end up working really well is if we sum forces in the normal direction equal to v squared over rho m times u hat n. So one other little tricky part of this problem. Let's maybe look at a free body diagram together. Let's pretend we're upside down at the peak of one of these loops. Right, so this is the most dangerous part of the track because you will have lost as much velocity as you're going to lose before you start to gain it again coming around the other side of the loop. So this is the part that we have to get by in order to make it through this loop. So forces acting on the body at this point are really just going to be mg and the normal force between the track and the body. Now, if we're going fast enough, if you're going really fast around a curve, do you feel as if you're being squished towards the outside of the curve or towards the inside of the curve? If you're, let's think about being in a car and you're taking a really fast curve. Do you feel as if you're being squished to the outside of the curve or towards the inside of the curve? The outside, right? So if you're going fast enough, there will be a force there's a force because of your motion that's wanting to spin you towards the outside, right? And if there's a track there, there should be a normal force that is equal and opposite to that squish, right? If you get slower and slower and slower, that force slinging you to the outside is going to be less and less and less and less. And so your normal force, which is keeping you on the track, is going to be less and less and less and less. And then at some point, you will not be going fast enough. At what happens to your normal force when you're just about to fall off the track? It goes to zero. Okay? So it is okay to be instantaneously zero, but any more than that, and you're actually going to start basically falling off of the track. Okay? So we need to solve for what velocity puts us at a normal force equal to zero. That is our constraint. We cannot go any slower than that, or we'll fall off the track.
Are these loops like right after each other? So they're really on three on B. Once they can go through B, it'll go through C.
Yes. Yes. We can prove it with math as well though. That so if you solve for like the height necessary at A to make it through B, it'll be a higher value than the height necessary at A to make it through C. So we can show that mathematically as well.
What's the other one? Is one for B, one for C, or just?
I believe your logic holds based on the conservation of energy that if it makes it through B, it will make it through C because it's a smaller height and you get all of your energy back. But because not everyone will pick up on that, I want to show it mathematically too. So I'm going to show that the height required to make it through B, and I'll show the height required to make it through C. And we'll say you have to choose the bigger height. Yeah. Mhm. Okay, the first thing that I did is I used the sum of forces in the normal direction equals mass times acceleration in the normal to find the velocity of the cart as it goes through B that will result in zero normal force. And then I did the same thing for point C. I found the velocity at C that will result in there being zero normal force. I actually kept them squared, mostly because we're going to need them squared when we use these within the conservation of energy equation. So, yeah.
If we're stuck in knowing what to do after, like the given find and free body diagram.
Yeah.
Should we make a free body diagram for each of the B and C to know like what forces? Does that make sense? Like for the sum of the forces
that,
in the
that
normal direction.
you can certainly draw separate free body diagrams, but they will be exactly the same.
Okay.
Yes, except that you could put like this is sub B and sub C and so on.
Never too late.
Never too late. What'd you get for your height, Micah? Good job. You got it too? Very good.
I use the other equation though.
The work energy, totally fine.
Just that balance over with the picture.
I feel like that's a good recommendation, but and I don't know that I've come up with a counterexample. But knowing the Hibbler book, I feel like there is probably some way that they could write a problem that is only solvable
With one.
with conservation of energy. I've yet to find it,
Okay.
but that's the only reason I continue to teach both is I can imagine a situation in which that might happen. So you should know both. Okay, so here I'm just checking that if I check for point C, does it require my height to be any higher than the height required to get through point B? You could logic your way into not needing to do this, but if that's not your forte, as sometimes it's not mine, I'm always hesitant to follow my own logic. That's fine. So let's do TA plus VA equals TC plus VC. Okay, so as long as the height of hill A is higher than 12.5 meters, we'll make it through C. But we have to be higher than 18.75 meters to make it through B. So we need to realize that this is our final answer, that height of hill A must be at least 18.75 meters to make it through both B and C.
I was just gonna ask, like, I think we did this.
Yeah, you
I
could,
don't need anything else.
you could just.
Say again?
We could still solve it if there was friction in the roller coaster.
Sure, because you have work energy.
Yeah.
Work energy would have worked. You couldn't have used the conservation of energy if there were friction involved. Correct. Okay, we finished a little early. I don't have any third question, but if you have any questions, I'm happy to stick around until we're
Can you,
through.
can you show us how to do the next part of this
Which part?
problem?
Which part?
You said we want to have time to do the normal forces on this
Oh,
problem.
yeah, okay. So,
Won't P then B just be zero?
yeah, so the
Because that's our
normal,
assumption.
correct. The normal force at B would be 0, but since our height is higher than required for C, our velocity at C will be greater than the minimum required. And so our normal force will be greater than the minimum required. So what we need to do is then repeat this part, the conservation of energy from A to C, taking H as known and the velocity at C as unknown. Okay, so we could do find VC given H equal to 18.75 meters. So we would have found A plus VA equals TC plus VC. That would still be 0. This would be 700 times 9.81 times 18.75 equals 1/2 mass times VC squared plus 700 times 9.81 times 10. Okay, and we would have solved for VC. I don't have it written down, and I'd rather tell you the logic of how to go from here than to take the time to calculate it. But we could solve this for the actual velocity happening at VC. And then we would need to go back to this line here. And instead of treating the normal as 0, we would treat the normal as unknown and plug in our new value of VC that we just solved for. Question, Samuel?
No, that's good. Thank you.
Does that make sense?
Yeah, and you don't know these answers?
I can find them fairly quickly. Let me look it up. This is 14.73.
I don't think I got it right. Got 17 kilonewtons.
Sorry, I think there's actually a bug with the solution guide, so I'm gonna calculate it myself. They appear to have plugged in the wrong number. So Okay, there's a 700 on all of these, so I'm gonna cancel that out. So we should have 9.81 times 18.75 minus 98.1 times 2 square rooted. I'm getting VC equals 13.102 meters
That's
per
what I
second.
got.
Okay. And then we should get an mg. Rho is 5. Okay, so n is our unknown, plus 700 times 9.81 equals 700 times 13.102 squared over 5. Can't subtract the 700. Okay, so 700 times 13.102 squared divided by 5 minus 700 times 9.81. I'm getting 17.165 kilonewtons.
Okay, I just thought that number was really big, so
Nope.
I was worried I got it wrong.
Okay, so they get the same final answer, but there's the solution guide is for sure from the book. Weird. Okay. Yeah, that's the correct final answer though.
Thank you.
You're welcome. Yeah, I probably should have just done that. Sorry. Thought we wouldn't have time, and usually I am correct. Okay, questions, comments, concerns? Nope. Okay, I'll see you tomorrow. Thanks, everyone.
Thank you, Dr. Higgins.
Bye.